Okay, for what we have in the next worksheet, test 4 review set, we have for problems 1 through 3, it says to find the exact value of x in each expression. And we have for the first problem, okay, we're looking at solving for x whenever 8 to the x plus 2 is equal to 4 raised to the 2x. And for what we have in this problem, okay, now 8 is a multiple of 4, but it is not an integer power of 4, okay, and we can rewrite both 8 and 4 in terms of a common base, okay, and that number is going to be 2 since 2 can multiply itself into both 4 and 8, and so just rewriting what we have for 8 and 4 along the lines of base 2, okay, so we have 8 is going to be 2 to the third, and so 8 to the x plus 2 is going to be 2 cubed raised to the x plus 2 degree. And for 4 to the 2x, again we have 4 is going to be 2 squared, and we have 4 to the 2x would be 2 squared to the 2x, and with the power property of exponents, okay, so for 2 cubed to the x plus 2, we have 2 raised to the 3 times x plus 2. For 2 squared raised to the 2x, we have 2 raised to the 2 times 2x. And we have with distributing, okay, so left hand side we're going to have 2 raised to the 3x plus 6, and we have is equal to 2 raised to the 4x. Now we have single base 2 terms, and we can set the degrees equal to each other. So we have 3x plus 6 is equal to 4x, and with 4x by itself, I can join that term with 3x, and we have, upon taking 3x away from both sides, we're going to have for the solution in x, we're going to have the value to be at 6. Okay, for what we have in number 2, we have a couple of base 2 logarithmic terms that will be added together, whereupon the sum will be equal to 3. And we're looking at solving for x that will fit into this equation. And again, for logarithmic terms, now the attachment has to be positive. So whatever we have for x, we want to make sure that x plus 1 is positive, and also that x plus 3 is positive. Now, for the sum of the logarithms, I can make what I have here into a single logarithmic term. And if you add logarithms together and you want to make into a single logarithmic expression, okay, we're going to multiply the attachments together. So I have base 2 logarithm of the quantity of x plus 1 times that of x plus 3, and we have equal to 3. And now, for the base 2 logarithm, I can eliminate the presence of this by treating both sides as powers to which the matching exponential base, which is 2, is going to be raised. So we have for the next step, we have 2 raised to the base 2 logarithm. And for x plus 1 times x plus 3, then we have x squared plus 4x plus 3. And we have is equal to 2 raised to the third power. So for 2 to the base 2 logarithm, the product of x plus 1 and x plus 3, okay, this will become x squared plus 4x plus 3. And to the right, have 2 raised to the third power, and 2 cubed is equal to 8. Okay, so we have a quadratic equation, and if I rewrite what I have and put into standard form, it's going to follow that we're going to have x squared plus 4x minus 5 is equal to 0. And taking what we have and factoring, so I have the quantity of x plus 5 times that of x minus 1 is equal to 0. Now we have 2 apparent solutions for x, and if I set x plus 5 equal to 0, we have that x is equal to negative 5. And if x minus 1 is equal to 0, okay, I have that x is equal to 1. Now upon checking, okay, whatever we have for x, you want to make sure that the attachments in the original logarithmic terms will be positive. So for negative 5 plus 1, that is negative 4. Negative 4 is not greater than 0, and automatically, okay, negative 5 is going to be disqualified. Now as for 1 plus 1 is 2, 2 is greater than 0, that is true. 1 plus 3 is 4, 4 is greater than 0, that is true. So there's going to be only one solution, and it's going to be with x is equal to 1. For number 3, okay, we have a couple of x terms here, whereupon we have the natural logarithm of the quantity of 2x minus 7 minus the natural logarithm of x is equal to 0. And for what we have in the attachments, again, we want 2x minus 7 to be positive, and for x to be positive. And now, for the difference of logarithmic terms, if I make into a single expression, okay, so subtraction is going to imply division. Okay, and so we will have the natural logarithm of 2x minus 7 over x is equal to 0. And if I get rid of the ln attachment, so ln is going to be a logarithm in base e. So I'm going to take e to the natural logarithm of this ratio. Okay, so I have e to the ln of 2x minus 7 over x, and that is going to be equal to e to the 0. And so we have left-hand side is going to be transformed to 2x minus 7 over x, and e to the 0 is equal to 1. And if I multiply both sides of the equation by x, so as to get rid of the fraction, we have that 2x minus 7 is equal to x, and then we have upon combining x terms together. So if I take 2x away from both sides, now we're going to have that negative 7 is equal to negative x, and if I change the signs at both ends, we have for the apparent solution x equal to 7. Now upon checking, 7 is greater than 0, that is true. And we have 2 times 7 is 14 minus 7 is 7, which is greater than 0, also true. So we do have one solution in the case of number 3, and that is with 7. Okay, for numbers 4 through 6, it says to evaluate the following expressions, round to the nearest 3 decimal places if the decimal does not terminate. Okay, so for what we have in numbers 4 through 6, okay, so you have a base 3 logarithm of 24. Now, in this particular case now, 24, it is a multiple of 3, but it is not an integer power of 3. And the only way we can determine, okay, this value or approximate the value is to use a change of base formula. And again, you can either use a natural or base 10 logarithm. And we'll go with the base 10 logarithm in this case. So we have the change of base formula. So we have base 10 logarithm of 24. We have divided by the base 10 logarithm of 3. And upon entering into your calculator, now you could use natural logarithms. I have like ln of 24 over ln of 3. But for what we have here, so we have for the base 10 logarithm of 24 divided by the base 10 logarithm of 3. And so to about the nearest 3 decimal places, this will be about 2.893. In the case of number 5, okay, we had the base 5 logarithm of e squared. And again, there are various ways that you can work with this. And I'll show you 2 different ways. If we go with the natural logarithm, okay, so you have the natural logarithm of e squared. We have all over the natural logarithm of 5. Okay, if you notice, you have the natural logarithm of e squared. And again, ln and e, these will match up. And we have this can go to 2 over the natural logarithm of 5. And so for 2 divided by the natural logarithm of 5, okay, that's going to go to 1.243 when rounded to the nearest 3 decimal places. And I just want to mention as well, or the base 5 logarithm of e squared. If I put this in terms of base 10 logarithms, we had the, in this case, base 10 logarithm of what is going to be e to the second divided by the base 10 logarithm of 5. And for what we're going to have in this case, all right, so you have base 10 logarithm of e squared divided by the base 10 logarithm of 5, and you still come out to the same result. So you have 1.243. In the case of number 6, okay, so you have base 6 logarithm of 216. And now 216, this is going to be both a multiple and an integer power of 6. In fact, 216 is going to be 6 raised to the third. So we have, in this rewrite, we had the base 6 logarithm of 6 cubed, and this will go to 3. And another way that you could look at this is that we can still apply the change of base involving natural and base 10 logarithms, and you can have something like the ln of 216 all over the ln of 6, or you just have log of 216 all over log of 6, and that reduction still goes out to 3.